NASA and SpaceX want Starship HLS to take huge payloads and eventually astronauts to the moon and beyond. To do that, they're betting big on in-orbit refueling. But what if there's another way? More than 60 years ago, scientists had an idea way ahead of its time, a massive lunar lander that could carry tons of cargo to the moon in one go, no refueling needed. Now imagine bringing that concept back, but upgraded with Starship's modern tech. What if adding just one more stage could turn Starship into a bigger breakthrough? Could this simple idea change the future of space travel? Why are both NASA and SpaceX still hesitant? Let's find out in today's TechMap episode. Things probably started off in the late 1950s and early 1960s, when Wernher von Braun and his team at NASA began sketching out some audacious ideas for how humans might travel to the moon. Among them were concepts for a family of enormous rockets, even more powerful than the Saturn V, that would eventually carry Apollo astronauts to the lunar surface. These proposals included lunar landers far larger and more capable than the Apollo lunar module. Von Braun envisioned spacecraft that could ferry 10 to 20 astronauts and as much as 60 tons of cargo to the moon vehicles designed to lift off from the surface without leaving parts behind in lunar orbit. The central idea was direct ascent launch, a single massive spacecraft straight from Earth to the moon, no docking or orbital refueling required. It's a fascinating concept. And it raises a natural question given Starship's scale and power. Could SpaceX essentially build a Nova-class rocket today? The answer is complicated, both yes and no. To conduct a direct ascent mission, a launch vehicle must carry all of its fuel and payload in one go. That demands staggering lift capacity. Nova was designed as a three-stage rocket, only a few meters taller than Saturn V, but much broader, 15 meters in diameter compared to Saturn's 10. By contrast, Starship measures just 9 meters across, yet its modern Raptor engines produce more total thrust than Nova's enormous F1s ever would have. Nova's first stage was expected to use 8 F1 engines, generating roughly 13.9 million pounds of thrust, 960-ton force. Super Heavy, in its version 2, exceeds that at about 8,240 tons of force. Nova's second stage, powered by 8 J2 engines, would have delivered 1.86 million pounds of thrust, less than half of what Starship's upper stage now achieves with 6 Raptors. On paper, Starship's performance seems to surpass Nova's. But there's a catch: Starship is heavier. Fully fueled, it tips the scales at about 4.9 million kilograms, compared to Nova's roughly 4.4 million. Even empty Starship is around 50 tons heavier. Nova's wider diameter and lighter mass also mean it could accommodate bulkier payloads, an advantage in a single-launch direct ascent architecture. So while Starship echoes Nova's ambitions, it isn't a one-to-one replacement. Von Braun's dream of a direct shot to the moon still demands a vehicle so large and capable that even today it remains just out of reach. The difference in weight between Starship and the Nova rocket largely comes down to purpose. Starship carries extra mass for controlled descent and landing heat shields, landing legs, and reserve propellant for deceleration and landing burns. Nova, by contrast, was designed to be used once and discarded. It didn't need this additional hardware or fuel, which made it lighter when empty. Even if Starship were expendable, as in the case of Starship HLS, it would likely still outweigh Nova. The reason lies in the materials. SpaceX builds Starship from stainless steel, while Nova's engineers planned to use lighter aluminum alloys. Stainless steel adds weight, but it offers critical advantages: high strength, excellent heat resistance, and the durability needed for reusability. Nova's design was optimized for one goal: maximizing payload to the moon, not for flying again. That distinction reflects how the priorities of spaceflight have shifted. In the 1960s, NASA pursued single-use rockets to achieve national prestige and scientific milestones. Today, commercial spaceflight is driven by cost cadence and sustainability. Reusability dramatically lowers launch costs, enables faster turnaround times, and increases flight frequency, crucial for everything from satellite deployment to science missions and eventually tourism. It also reduces waste and helps curb the accumulation of space debris. SpaceX recognized this shift earlier than anyone. The company bet that reusable rockets would define the future of launch services, and that bet has paid off. SpaceX's rapid growth both in revenue and launch cadence stems directly from its reusability strategy. The company now delivers more payload to orbit than any other organization on Earth, solidifying its reputation within NASA, the White House, and Congress for saving the U.S. government billions in launch costs. This dominance also carries geopolitical weight. By leading the world in orbital lift capacity, the United States strengthens its position in the global space market, leaving China, its most ambitious rival, playing catch-up. China, for its part, has begun developing reusable rocket systems, recognizing that the future of access to space depends on flying hardware more than once. Meanwhile, the legacy aerospace firms that built the old space industry have struggled to adapt. United Launch Alliance, for example, has faced financial strain as its traditional expendable rockets became too costly to compete. Now, even ULA is pursuing partial reusability, working to recover the engine section of its next-generation Vulcan rocket, a tacit acknowledgement that the era of throwaway rockets is coming to an end. For a large national space agency like NASA, though expendable rockets still have their place. They offer the maximum possible payload capacity and avoid the complexities of orbital refueling or recovery operations. For certain missions, those that fly infrequently or involve specialized payloads, an expendable vehicle can actually be simpler and, in some cases, cheaper. There's no need for refurbishment landing gear or the infrastructure required to recover and reuse hardware. So does that mean NASA should consider reviving the NOVA concept now that modern technology could make it feasible? The answer almost certainly is no. Unlike the Space Launch System, which reuses parts of the Space Shuttle's design and existing industrial base, NOVA would be entirely new, a massive rocket built from the ground up. That kind of project would require vast funding, years of development, and a level of political commitment that's rare in modern Washington. It's far more practical for NASA to leverage launch systems already developed by private companies. SpaceX's Starship, for example, can evolve, iteratively improving performance over time without the bureaucracy and cost of a government-led development cycle. And if a mission ever demands maximum payload to orbit, a reusable rocket like Starship can operate in an expendable configuration, sacrificing recovery for capability. In essence, the logic that once drove the NOVA program, sheer power at any cost, has been replaced by a new philosophy: flexibility, efficiency, and partnership with industry. NASA no longer needs to build the biggest rocket in the world. It just needs to use the best one available. NASA's modern exploration strategy looks very different from the era of NOVA. Today, the agency favors a modular, incremental approach, dividing big objectives into smaller, carefully planned steps. Rather than one colossal launch carrying everything at once, payloads are spread across multiple missions and vehicles. The goal is to make deep space exploration safer, more flexible, and ultimately more sustainable. This strategy also allows NASA to take advantage of the strengths of its commercial and international partners. The Artemis program illustrates this well. Astronauts will travel to lunar orbit aboard NASA's Orion spacecraft, launched by the government-built SLS. Meanwhile, other rockets, often provided by private companies, will deliver cargo surface habitats and lunar landers. SpaceX's Starship human landing system, for instance, will carry astronauts from lunar orbit down to the surface at a fraction of the cost of traditional government hardware. By distributing responsibilities among multiple partners, NASA taps into a wider pool of innovation while sharing costs and risks. The agency also deepens collaboration with allied space agencies, building a truly international effort. Each Artemis mission builds on the last, starting with simple flybys and lunar orbits, then progressing to surface landings, outposts, and eventually long-duration stays. If engineers ever wanted to push Starship into truly Nova-class territory, one intriguing idea would be to add a high-energy third stage, something like ULA's Centaur 3. This upper stage uses liquid hydrogen and oxygen propellant, an exceptionally efficient combination for deep space missions. Hydrogen offers a high specific impulse, making it ideal for sending payloads beyond Earth orbit to the Moon or even Mars. It also aligns with future in-situ resource utilization concepts, since hydrolox could eventually be produced from lunar ice. Starship, of course, was designed with Mars in mind. Its Raptor engines burn methane and oxygen, a choice driven by the potential to synthesize methane on the Martian surface. But for lunar operations, hydrogen has clear advantages. Centaur's engines also offer precise control with the ability to start-stop and restart multiple times during flight. That flexibility is valuable for complex trajectories and course corrections. And with decades of proven reliability on Atlas rockets, Centaur represents a well-understood technology base. However, marrying Centaur to Starship would be far from straightforward. The two systems were designed for entirely different architectures. Integrating them would introduce major engineering challenges, different fuel types, thermal requirements, and structural interfaces. A Centaur-derived stage would also add significant mass and complexity, potentially reducing Starship's payload capacity. Then there's the issue of reusability. Centaur is built for expendable missions, while Starship's entire value proposition is its ability to fly again. Combining the two could undermine that advantage, driving up costs and negating much of what makes Starship revolutionary in the first place. In the end, the concept of a Nova-class Starship is fascinating from an engineering standpoint, but in practical terms, it might be a step backward. SpaceX's philosophy leans toward iterative innovation and operational efficiency, not bolting legacy hardware onto next-generation systems. ULA has been working on a rocket stage called Centaur for many decades, since the 1960s, which shows a lot of experience and trust in their designs. The Centaur stage is like a powerful engine booster that helps push satellites and spacecraft into higher orbits or on trips to the Moon and beyond. It uses super-efficient fuel liquid hydrogen and liquid oxygen that gives it a lot of power with less weight, which is really important for reaching space. Centaur can turn its engines on and off multiple times during a mission, so it can carefully guide the spacecraft to different places instead of just going in a straight line. The Centaur stage is built very light but strong, using thin metal tanks that can handle very cold fuels, allowing it to carry more useful cargo without adding extra weight. ULA also built a bigger version called Centaur 5 for their new Vulcan Centaur rocket, making it even stronger for heavier loads. Catching a moving rocket with a launch tower still feels surreal even after seeing it happen. The so-called Mechazilla system at Starbase has become one of the most striking examples of SpaceX's engineering ambition. But for all its spectacle, it raises an obvious question about the company's ultimate goal. What happens when Starship tries to land on the Moon or Mars? There's no concrete pad, no steel tower waiting to cradle the vehicle. Lunar and Martian surfaces are rough, unpredictable, and covered in dust and rock. Any rocket hoping to touch down safely will need to stand on its own. That's where landing legs come in. SpaceX already has deep experience in this area. The Falcon 9's carbon fiber and aluminum honeycomb legs have proven themselves hundreds of times both on land and at sea. But scaling that approach to Starship is an entirely different challenge. Starship HLS, the version designed for lunar missions, is vastly larger and heavier. Instead of 4 lightweight legs, it will likely require 6 made from high-strength stainless steel. The trade-off is obvious: more mass. Every extra kilogram devoted to structure is 1 less for fuel or payload. Engineers are still studying just how many legs Starship will need. Some designs suggest 6, others perhaps 8. The reason is stability. Unlike the drone ships that Falcon 9 lands on the Moon, offers no guarantee of a flat surface. Craters, slopes, and loose regolith make even a small tilt risky. With a vehicle nearly 50 meters tall, a few degrees of imbalance could prove disastrous. More legs help distribute the load, but they also add complexity. Each one must deploy lock and retract flawlessly. A single jammed hinge could end a mission. And because there's no ground crew on the Moon or Mars, every operation must be autonomous and fail-safe. Then there's the problem of the engines themselves. The Raptor engines are incredibly powerful. We've already seen them pulverize a reinforced concrete pad in Texas. On the Moon, where there's no atmosphere to slow debris, plumes could blast rocks and dust directly into the vehicle's stainless steel skin or into sensors, or even ricochet into the engine bells themselves. All of this highlights one of SpaceX's biggest hurdles with Starship HLS. The company can design towers to catch rockets on Earth, but beyond it, Starship will have to catch itself. Landing on the Moon and Mars isn't optional for Elon Musk's long-term vision of a multiplanetary future, it's essential. That makes solving the landing challenge one of SpaceX's highest priorities. Adding landing legs comes with an unavoidable cost. More structure means more mass. But SpaceX seems willing to accept that trade. For missions beyond Earth, stability and crew safety outweigh almost everything else. Engineers are already looking for ways to minimize the penalty. Advanced materials like the same high-strength stainless steel that forms Starship's body can keep the system robust without adding too much weight. Smart mechanical design will play a part, too. One concept under consideration is a telescoping leg design. In this approach, the legs remain folded tightly against the vehicle during flight, then extend outward and downward in the final seconds before landing, much like a collapsing spyglass snapping open. Another idea involves crush cores, essentially built-in shock absorbers. They're designed to deform slightly on impact, soaking up the final jolt of touchdown and protecting the vehicle's structure from excessive stress. Back on Earth, SpaceX can take advantage of its Mechazilla tower and rapid reuse philosophy. Even if lunar or Martian missions carry less payload per flight, faster turnaround times, and lower overall launch costs can balance the equation over the long term. And it's worth noting, not every Starship will have to make the return trip. NASA's Human Landing System version, for example, is expected to serve as a one-way lunar lander. That gives engineers more flexibility. They can afford to make the legs heavier, stronger, and more specialized for the Moon, since they don't have to worry about bringing that extra mass home. To keep Starship upright during touchdown, SpaceX has been experimenting with deploying several widely spaced landing legs that fold neatly against the rocket's body during ascent, then swing outward and lock into place just before landing. The retractable design serves a dual purpose. It protects the legs from the blast of superheated plasma during re-entry and keeps the vehicle's exterior smooth and aerodynamic during flight. At the base of each leg, small actuators initiate the deployment sequence. These devices nudge the telescoping assemblies outward, allowing them to slide and lock into position with precision. What remains uncertain is exactly which kind of actuator SpaceX will settle on. Early concepts considered using high-pressure helium to power pneumatic actuators similar in spirit to the system that drives Falcon 9's smaller landing legs. In principle, it's simple and lightweight. But in practice, scaling that approach to Starship's enormous mass and lunar landing requirements isn't realistic. The forces involved are far greater, and helium-powered mechanisms would likely lack the strength and redundancy such missions demand. Hydraulics have also been on the table. They're robust and can absorb hard impacts or compensate for uneven terrain qualities well-suited for rough lunar or Martian surfaces. The trade-off, however, is complexity and risk. A single leak or ruptured line in vacuum could cripple the system, and repairs wouldn't be an option 400,000 kilometers from Earth. That leaves one increasingly promising path: electromechanical actuators. This approach aligns with SpaceX's broader trend toward electrification, borrowing concepts from Tesla's vehicle technology. Electric motors offer precise control, consistent reliability, and eliminate the need for consumable gases. They're also far easier to monitor and maintain across multiple flights. Alongside these actuators, engineers are likely to integrate shock-absorbing components, crush cores, as said, or other energy-damping systems to cushion Starship's landings on rough terrain. Together, these mechanisms represent one of the spacecraft's most intricate engineering challenges: a landing system that's compact, durable, and smart enough to handle worlds without runways. To help guide Starship safely to the surface, SpaceX plans to rely on an array of cameras and sensors that will allow the vehicle to effectively see its landing site. These instruments will scan the terrain in real time, identifying hazards like boulders, craters, and steep slopes before touchdown. The goal is simple: find the safest, flattest spot possible, and avoid the kind of surprises that could turn a routine landing into a mission-ending accident. One of the biggest concerns for any lunar landing is the power of the rocket's own engines. The Raptor engines are immensely powerful, more than capable of blasting loose rocks and dust upward with enough force to damage the vehicle or nearby equipment. To counter this, SpaceX's lunar variant of Starship will use a clever workaround. Rather than firing its main Raptors all the way to the surface, the spacecraft will switch to smaller thrusters, mounted higher on the body near the nose. These engines provide the final braking impulse, keeping the exhaust plume far from the lunar ground and minimizing the risk of regolith being thrown back into the vehicle. The same principle will eventually extend to Mars, though the environment there introduces a new set of challenges. The thinner atmosphere means dust and debris will behave differently, still dangerous but somewhat more predictable. Engineers expect the risks to be manageable, especially with experience gained from early lunar missions. At this point, one question naturally arises: if landing on legs presents such a major engineering challenge, has SpaceX considered doing away with them altogether? As it turns out, the company has. During a Flight 10 webcast earlier this year, an attempt ultimately scrubbed due to weather, SpaceX spokesperson Dan Hewitt offered an intriguing comment about future Mars missions. They're just going to put minimally viable landers on the surface land, right on the skirt, no landing legs, he said. The remark was later cited in Space.com's coverage following the successful Flight 10 test. It's an idea that sounds bold, but not entirely unrealistic. The Moon's gravity is roughly 1/6 that of Earth's, meaning Starship would weigh dramatically less there. That reduction opens the door to the possibility of landing directly on its base, the broad stainless steel skirt that houses the engines without the added mass and complexity of a traditional leg system. Engineers have also floated other creative concepts. One involves using small thrusters to stabilize the vehicle during the final seconds of descent, while another explores deploying prefabricated landing pads ahead of time to create a smoother touchdown zone. All of these remain under study, and none have yet proven more practical than the simplest solution: sturdy, extendable landing legs. Even in weaker gravity, the Moon's surface is unpredictable. A broad base can help, but a set of well-designed legs still provides the best insurance against a slow tip-over that could end a mission in seconds. So how about you? Either legs or not leg, which one do you like better? Let me know in the comments section below. SpaceX isn't standing still on the landing leg issue. Ground testing of Starship's landing systems is expected to begin within the next year, possibly by late 2025 or early 2026. These trials will be crucial to validating the structural integrity deployment mechanisms and shock absorption systems before any lunar flight demonstrations can proceed. With NASA's Artemis 3 mission on the horizon, the timeline puts considerable pressure on SpaceX to move quickly. In early September, close observers noticed something new taking shape at SpaceX's McGregor facility in Texas, the same site where Raptor engines are manufactured and tested.
On August 27, 2025, just after sunrise, SpaceX launched another batch of 28 Starlink satellites into orbit using a Falcon 9 rocket. Nothing unusual there, except this flight also marked a big milestone: the 400th successful drone ship landing of a reusable Falcon 9 booster. Pretty impressive. Now, SpaceX has been landing rockets on drone ships for years, and there's many good reasons for it. A lot of people assume that for a rocket to reach space, it just needs to go straight up. After all, rockets launch vertically and space is up, right? But getting to space isn't quite that simple. To actually stay in space, a rocket doesn't just go up. It has to go really fast forward. Think of it like this. To escape Earth's gravity and stay in orbit, you have to be moving sideways so quickly that you're essentially falling around the Earth instead of back down to it. That's why rockets launch straight up at first, to get through the thickest part of the atmosphere, but then they tip over and fly more horizontally, like a plane on steroids. So why land the rocket on a ship in the middle of the ocean? Well, by the time the first stage of the rocket has done its job and separated from the second stage, it's already way downrange, far from the launch pad and moving incredibly fast. Flying it all the way back to land would cost a ton of fuel and money. Imagine jumping off a swing while it's moving forward and trying to land behind the swing set. It's just not practical. Instead, SpaceX positions a drone ship out in the ocean, right about where the booster would naturally fall, and lands it there. From a business perspective, this is smart. SpaceX is basically a delivery company for space, and reusing boosters saves them a fortune. Refurbishing a landed booster is way cheaper than building a new one from scratch. Even when you factor in the cost of the drone ship and its crew, it's still a huge win. Could they land back on land instead? Sure, and they do when the mission allows it. But landing on land takes more fuel, and every extra pound of landing fuel is a pound you can't use for your payload. So if you're launching something really heavy or sending it far, it's actually cheaper to just land the booster out at sea. There's also a neat bonus: flexibility. By using drone ships, SpaceX can launch bigger satellites or send missions deeper into space without worrying as much about fuel limits. It opens up a lot more options. Oh, and there's a safety angle too. If they change things around so the booster came back down over land, say in Europe, Africa, or some remote island, any failure could send debris over people's homes, even with a flight termination system. Landing in the ocean is just safer for everyone. It's pretty clear that landing rockets on drone ships comes with a lot of benefits. Just look at how successful it's been with Falcon 9. So it's kind of surprising we haven't seen the same thing happening with Starship yet. But don't worry, that option is definitely still on the table. According to an FAA document, Super Heavy, the booster for Starship, could either land on a drone ship or be expended in the Atlantic Ocean. Starship itself might also land on a floating platform or be ditched in designated landing zones. One of those zones, by the way, is in the Pacific Ocean, just outside the U.S. Exclusive Economic Zone. The idea of drone ship landings was actually reviewed as part of the 2025 National Marine Fisheries Service consultations. So this isn't just theoretical. It's already being planned for. There's even a near-shore backup landing zone in the Atlantic, starting about 1 nautical mile off the coast and stretching up to 50 miles, both north of Kennedy Space Center and south of Cape Canaveral. If Starship or Super Heavy does land on a floating platform downrange, the plan is to bring them back to Port Canaveral by barge, then move them the rest of the way using existing roads through the turn basin. So what would SpaceX actually need to land a Starship on a drone ship? Well, first things first, they'd need a drone ship, obviously. SpaceX drone ships are uncrewed, rocket-powered ocean barges designed to catch rockets. They have built-in propulsion systems that let them stay precisely in position out at sea, all on their own. These ships are used to recover Falcon 9 and, eventually, Starship boosters after launch, especially on missions where returning to the launch site isn't possible due to fuel constraints. Each drone ship is equipped with GPS azimuth thrusters, a reinforced landing platform marked with that signature X, and an octograbber, a robotic system that secures the rocket after landing. This setup is what makes SpaceX's rapid reusability possible. Right now, SpaceX operates 3 autonomous spaceport drone ships. Just read the instructions: a shortfall of gravitas and, of course I still love you. Just read the instructions. And a shortfall of gravitas are based at Port Canaveral and support launches from Kennedy Space Center and Cape Canaveral, with landings in the Atlantic Ocean. Of course I Still Love You is based at the Port of Long Beach and supports launches from Vandenberg Space Force Base, with landings in the Pacific. Depending on the mission, SpaceX can either bring the booster back to the launch site for a ground landing, land it out at sea on one of the drone ships, or discard it entirely if recovery isn't worth it. But here's the thing. Those drone ships were all designed for Falcon 9. Starship is much, much bigger. So there's no current drone ship that can handle it. That's where something new comes in. On September 16, 2025, Elon Musk confirmed that SpaceX is developing a new vessel, a water ship, to transport Starships from Starbase in Texas to Cape Canaveral in Florida. He actually teased it a week earlier with a cryptic "You'll thank me later" post, which seems to continue SpaceX's tradition of giving its ships sci-fi-inspired names, often drawn from I.N.M. Banks's Culture series. The main job of this new watership is to transport Starships horizontally by sea, helping support upcoming launches from Kennedy Space Center's Pad 39A and Launch Complex 37. With plans to launch and land up to 44 Starships and Super Heavy boosters per year, SpaceX needs an efficient way to move these massive rockets. And sea transport helps reduce the logistical headaches that come with moving something this big over land. But don't forget that this watership, at least for now, is just a transport ship. It's not built for rocket landings. So if SpaceX wants to recover Starship at sea the way it does with Falcon 9, it'll either have to heavily modify this ship or build a whole new kind of drone ship, one that can handle the size, weight, and power of the biggest rocket ever built. It might be possible to land a Super Heavy booster on a massive autonomous drone ship, ADSP, but it's definitely not something to take lightly. There are 2 main options, and each comes with some pretty big challenges. One possibility is to modify Super Heavy to have landing legs. But at around 200 tons, adding legs isn't just a simple bolt-on job. We're talking about substantial hardware, likely many tons just for the legs themselves. On top of that, you'd need extra propellant to lift that added weight in the first place, even more to decelerate it on the way down, and yet more to launch the fuel that slows it down. It quickly adds up to a significant cost in both launch mass and development time. Now, when it comes to Starship itself, the good news is that at least the early versions heading to the Moon or Mars will already be equipped with landing legs. So SpaceX has to design for that capability anyway. In fact, back in the SN 15 days, they actually performed successful landing tests using prototypes with legs, so that data still exists and could be leveraged. If SpaceX really wants to avoid carrying the extra weight of legs on Super Heavy, the other option is building a catching tower directly on the ADS-B. But doing that in deep water adds another layer of complexity. A tall structure like that would be subject to sway, pitch, and roll, especially 50 to 60 meters above sea level. Even with partially flooded legs to help stabilize the platform, movement at sea level tends to get amplified at height. That said, a tower could offer more stability overall. The booster could be quickly secured after landing, which is important. Falcon 9 stages have toppled on drone ships in rough seas before. The launch site for Starship is Boca Chica, located on the Gulf, which is generally calmer than the Atlantic. The port of Brownsville, a deep water port, is just 30 kilometers from the Starbase production facilities. Right now, Super Heavy is transported about 4 kilometers by road to its launch site. If Boca Chica Boulevard were expanded into a proper two-way route, that same road could potentially be extended all the way to the port without causing too much disruption for locals. Similar to Falcon 9, the drone ship would return to a purpose-built dock near Boca Chica, where Super Heavy could be offloaded, refurbished, and prepped for its next launch. Honestly, when we talk about drone ships, there's one more thing that needs to be addressed. Marine assets kind of suck. Let me explain. The SpaceX drone ships in Florida are supported by additional vessels that assist with operations and also help recover payload fairings. These support ships are named Bob and Doug after the two astronauts from the first Crew Dragon mission to the ISS. Usually, SpaceX hires a tugboat to tow the drone ship out to its landing position and back again. Once everything's in place, it's supposed to be a well-oiled machine, running on a regular schedule. But of course, things are never that simple when it comes to marine operations. For starters, ship crews often work for weeks or even a month straight without a break, but eventually they need downtime. The same goes for the ships themselves. They need regular maintenance, repairs, and the occasional upgrade. On top of that, weather is always a wild card. If the conditions at sea aren't safe, the entire mission could be delayed. Even when the weather is technically acceptable, it can still slow down the trip to and from the landing zone. Then there's the cost. Marine assets are expensive. Bob and Doug probably cost around $10 to $20 million each per year to operate. The drone ships? Likely in the same ballpark. Maybe even more when you factor in tug services. The thing is, they cost almost the same just sitting at the dock if you're not flying. Marine ops just add a ton of complexity, cost, and unpredictability. Now let's bring Starship into the picture. Transporting a landed Super Heavy booster back from sea would mean it's out of commission during that whole trip. And while that might sound reasonable to us, Elon Musk is laser-focused on rapid reusability with minimal downtime. Waiting days for a sea recovery doesn't fit that vision. So what does all this mean? Landing Starship on a drone ship shouldn't be the primary method of recovery. It's just not efficient enough for regular operations. But, and this is important, it would be a great backup or supplemental option. Most routine Starship missions, like launching Starlink satellites, would ideally return to the launch site and be caught by the Mechazilla tower. Quick turnaround, minimal fuss. But as we've talked about before, there's a big trade-off between bringing the booster back to land and sending it farther downrange to a drone ship. Downrange landings allow for heavier payloads and higher energy missions. Take Artemis 3, for example. That mission would benefit a lot from the increased performance of a downrange landing. To support something like that, SpaceX may end up building a dedicated Super Heavy-class drone ship. Why? To refuel the lunar depot faster and reduce the number of tanker flights needed for a mission like Artemis.
In essence, a permanent lunar base is humanity's next foothold beyond Earth, something like a small town or research outpost planted on the moon. The concept isn't science fiction anymore. It would include habitats for astronauts to live and work, along with labs for scientific research. Power would come from solar arrays stretched across the gray regolith, or perhaps compact nuclear reactors humming quietly through the lunar night. To sustain life systems would recycle air water and waste, allowing crews to stay for months or even years at a time. The motivation goes beyond mere exploration. Because the moon's gravity is just 1/6 that of Earth, it offers a convenient launch point for missions deeper into the solar system. Astronauts could test technologies needed for Mars expeditions while studying the moon's geology up close. There's also a practical advantage: the moon itself holds valuable resources. Water ice trapped in its polar craters could be turned into drinking water or rocket fuel. Mining lunar materials means less dependence on costly supply runs from Earth, a major step toward sustainable space operations. That's why nations with serious space ambitions are setting their sights on establishing a lunar base. China, partnering with Russia and others, aims to build one by the 2030s. Their vision includes laboratories, mining infrastructure, and reliable power systems, possibly nuclear. Officials in Beijing have hinted at welcoming international cooperation on their terms. The United States, of course, isn't sitting idle. NASA views the moon as both a proving ground and a strategic necessity. The competition has sharpened since China's Chang'e 6 mission planted flags on the lunar surface in June 2024 using material collected from basaltic plains. The message was unmistakable: they're coming. For Washington, that has added a renewed urgency to get American astronauts not just back to the moon, but to stay there. Under President Trump's direction, NASA was given a clear mandate: return Americans to the moon. The effort, known as the Artemis program, includes plans not just for short visits, but for building a lasting foothold there, a lunar base called Artemis Base Camp. In broad strokes, Artemis 3 will resemble Apollo 11, a flags and footprints mission meant to prove the agency can once again land humans on the moon. Artemis 4, however, marks the real turning point. That's when NASA intends to begin assembling the first elements of a permanent outpost, habitats, power systems, and the tools needed for longer stays on the surface. If Artemis 3 moves ahead on schedule, it gives NASA more time to focus on preparing the next, more ambitious step. This urgency helps explain why the agency has placed such high expectations on SpaceX and its Starship human landing system. NASA sees the company's rapid, iterative approach as essential to keeping the timeline intact. So when SpaceX misses deadlines, frustration inevitably follows. That tension has spilled into public view. In recent weeks, acting NASA Administrator Sean Duffy has criticized SpaceX's progress on Starship, warning that delays could threaten the Artemis schedule. He's even hinted at opening up the lunar lander contract to other contenders, names like Blue Origin and Lockheed Martin. Elon Musk, never one to hold back, has bristled at the criticism. The SpaceX founder, whose ambitions stretch well beyond the moon, has taken shots at Duffy on social media, questioning his understanding of how innovation actually works. Critics inside and outside the agency argue that opening up the Artemis lander competition to new entrants could actually slow progress. Blue Origin, despite its growing ambitions, still lacks a meaningful track record in human spaceflight. Awarding such a high-stakes contract to a company with limited experience, they say, risks adding years of delay. SpaceX, by contrast, has already poured billions of its own dollars into developing Starship, a fully reusable vehicle intended for deep space missions. Its pace is unmatched in the industry. Even NASA officials privately acknowledge that no other contractor has demonstrated comparable speed or willingness to take financial risks. That stands in stark contrast to the old guard of aerospace. Lockheed Martin, for instance, has long benefited from cost-plus contracts that guarantee profit regardless of performance. The Orion spacecraft, Lockheed's flagship project for NASA, has suffered repeated delays and ballooning budgets. If Lockheed were to receive a new lunar lander contract under similar terms, the fear is that history would repeat itself, leaving taxpayers footing the bill for another slow-moving program. For Elon Musk, the deeper issue isn't just who builds the lander, it's how NASA approaches the moon altogether. He has been blunt in his assessment of Artemis, supposing it overly bureaucratic and unnecessarily drawn out. In Musk's view, waiting until Artemis 4 to begin constructing a permanent lunar base is a missed opportunity. Why, he asks, spend years retracing Apollo's footsteps when technology now allows us to stay? Elon Musk has offered what he believes is the simplest path: forward one rocket to do it all. That rocket is Starship. With a payload capacity exceeding 200 metric tons to orbit in the fourth version, Starship could fundamentally change how we build on the moon. Musk envisions the vehicle as both a workhorse and a habitat, capable of carrying the heavy cargo needed to assemble a base soon. In his plan, commercial cargo missions to the moon could begin as early as 2028, at a cost of about $100,000 per kilogram. For comparison, previous lunar deliveries cost roughly $1 million per kilogram. That's a tenfold reduction, the kind of leap in affordability that might finally make a permanent lunar settlement feasible. But Musk's concept goes further than logistics. He imagines a version of Starship that doesn't just ferry materials, it stays. Stripped of wings and heat shields, the lunar variant would remain permanently on or near the moon, serving as a flexible and modular base of operations. After landing vertically, the ship could tilt to a horizontal orientation, transforming into a habitat. Robotic systems would assist in refitting the interior, adding floors, walls, electrical systems, plumbing, and thermal controls, turning the spacecraft from a transport vehicle into a livable home. Inside, the design favors openness and efficiency. A single continuous deck running the length of the ship, divided into zones for sleeping, dining, research, exercise, and maintenance. Living quarters would be arranged to provide privacy and mimic Earth's day-night cycle, while common areas would help maintain crew morale. Power would come from 5 large solar arrays, each about 18 meters in diameter, deployed in a hexagonal pattern around the base. Life support systems would operate in a closed loop to conserve air and water. For protection against radiation and micrometeoroids, Musk's team proposes covering the ship in a 5-meter layer of lunar regolith, turning it into a bunker of sorts, a steel and dust fortress on the moon. SpaceX's vision for a lunar outpost represents a fundamentally different way of thinking compared to NASA's Artemis base camp, where the government program leans on decades of traditional engineering, prefabricated modules, incremental assembly, and a carefully choreographed rollout. SpaceX aims for something faster, simpler, and arguably more elegant. The core idea behind what Musk calls Moonbase Alpha is speed and efficiency. There's no need for a construction crew melting lunar dust into bricks or assembling habitats from a pile of crates. Instead, the base is the rocket itself. Land a Starship, tilt it horizontally, refit the interior, and it becomes a home. The design leverages the ship's existing structure, carrying everything needed for habitation on board from the start, then using lunar regolith as a natural shield against radiation. It's an approach that skips years of planning and surface construction. In Musk's view, the quickest route from landing to living. Flexibility is another advantage. Each Starship can operate as a self-contained habitat or link together with others to form a larger settlement. Expansion is as simple as landing another vehicle. By contrast, NASA's Artemis Base Camp envisions fixed surface modules that must be pre-built, tested, and delivered individually, a process that adds cost, time, and logistical complexity. The difference ultimately comes down to philosophy. Artemis relies on a traditional government-style architecture, a patchwork of components built by multiple contractors, each serving a specific role. SpaceX, meanwhile, proposes an integrated system designed from the ground up for reuse and scalability. It's an audacious idea, but it fits Musk's pattern: identify the bottleneck, strip away bureaucracy, and build something big enough to change the equation entirely. Whether NASA will embrace that simplicity, however, remains an open question. NASA's deliberate step-by-step approach to Artemis may look methodical on paper, but some see it as the very reason the United States is falling behind China in the race to establish a lunar base. Beijing's plans are moving faster and with fewer bureaucratic layers, aiming directly at a permanent outpost by the 2030s. The reason for NASA's slower pace is already visible. The agency's sprawling architecture, divided into multiple phases, each with its own contractors and hardware, has created fertile ground for political and corporate interests. As Ars Technica's Eric Berger has pointed out, some of the program's most expensive components seem driven less by engineering necessity than by politics and profit. One example is the Exploration Upper Stage, or EUS, that will debut on the SLS's Block 1B rocket during Artemis 4. The upgraded stage costs about $700 million per unit. A comparable upper stage, ULA's Centaur 5, could perform similar missions for under $120 million. The difference, Berger noted, isn't about capability. It's about contracts. Boeing, which builds the EUS, operates under a cost-plus arrangement that reimburses expenses and adds guaranteed profit on top, regardless of delays or overruns. As Berger, being in response to a question from everyday astronaut on social media, NASA's insistence on developing the EUS appears to have less to do with exploration and more to do with keeping money flowing to Boeing and sustaining jobs at Kennedy Space Center. It's a reminder that even in humanity's next great leap, outward old habits and old contracts still weigh heavily. The dream of building a base on the moon is hardly new. It's an idea that has lived in the human imagination for more than a century. In the late 1800s, writers like Jules Verne with From the Earth to the Moon, 1865, and Herbert George Wells with The First Men in the Moon, 1901, first gave shape to the vision, inspiring generations of scientists and engineers to turn fiction into fact. By the 1950s, Wernher von Braun helped translate that dream into a practical roadmap: space stations, a lunar base, and eventually a human mission to Mars. His ideas shaped the early era of space exploration and laid the groundwork for what became the Apollo program, culminating in humanity's first footsteps on the moon in 1969, an achievement driven as much by Cold War rivalry as by scientific curiosity. On December 11, 2017, when the White House signed Space Policy Directive 1, formally tasking NASA with returning humans to the moon. This new directive marked a strategic shift, one that opened the door for commercial partnerships to share the work and cost of deep space exploration. Out of that policy came Artemis, NASA's new lunar program announced later that year. The first time we ever got a look at Starship HLS was back in April 2021. That was when SpaceX officially landed the NASA contract for the Artemis missions. The design at the time looked like your typical Starship, just without the aerodynamic flaps or the heat shield tiles. Instead, it came with a few unique touches: things like a crew elevator and solar panels wrapped around the nose. But one big mystery still lingered. What does it actually look like inside? For a while, that question didn't have an answer. Over the years, though, things started to come into focus. Then, in late October 2025, SpaceX dropped what is the official design concept for NASA, and this time we finally got a good look within. The new update shows a single expansive cabin, the main pressurized living and working space for the crew. It's huge, about 600 cubic meters in volume. To put that in perspective, that's roughly 2/3 of the entire pressurized volume of the International Space Station, and more than 130 times what the Apollo lunar module offered. That kind of space opens up a lot of possibilities room. For supplies bunks, a command and control station, and still plenty of room to move around. That brings us to SpaceX's first true HLS prototype, the one that went viral back in November 2024. You might remember the photos from Starbase. This full-scale mock-up sat there for over a year, built to demonstrate the basic functionality of a few HLS systems. Think of it as a subscale test version, not meant to fly, but to show how the real thing might work. In general, both this early prototype and the latest design share a similar layout, 2 decks connected by an elevator. But beyond that, the differences are striking. Inside the subscale HLS prototype, the interior feels cramped. The space is divided into 2 small rooms, each one packed with exposed cables, machinery, and narrow walkways. Even the ladder between decks is tight and mechanical, more like a maintenance bay than a crew habitat. The new design, on the other hand, feels completely different. It's open, clean, and far more refined. The walls curve smoothly with the shape of the rocket, and most of the equipment and storage are tucked away behind sleek panels. Instead of feeling crowded, the cabin feels spacious. A wide central staircase connects the decks, giving astronauts plenty of room to move, and making the interior feel much larger than before. Then there are the windows, big, wide views, looking straight out onto the moon. They're not just for the view either. They help with visibility during landing. Still, there's something poetic about being able to look out at the lunar surface from your cabin window. The lighting, too, has been rethought. It's soft-built right into the walls and casts a gentle glow without harsh shadows. The furniture and seating hug the walls, leaving the center space clear, perfect for astronauts to float and work freely in zero gravity. So why do the prototype and the official Starship HLS look so different? It all comes down to what the prototype actually was. The mock-up was built inside Starship S-22, a vehicle originally designed to hold fuel tanks, not people. That meant the internal volume was limited from the start. The structure was narrow, and a lot of the available space was taken up by plumbing and equipment. In other words, it was never meant to be comfortable, just functional. SpaceX built it as a test bed, a way to study different layouts, test crew operations, and evaluate ergonomics in a realistic environment. After collecting feedback from NASA and astronaut crews, SpaceX went back to the drawing board. The result was a full redesign, this time optimized from the start to be a livable space. The improvements focus on comfort, efficiency, and accessibility, all while keeping the same mission goals intact. It's a great example of SpaceX's design philosophy in action: build, test, improve, polish, and then do it all over again. Now, beyond its open interior, which offers roughly 600 cubic meters of pressurized space, the Starship HLS also includes 2 dual airlocks for surface exploration. If you're not familiar with the term, an airlock is essentially a small chamber that acts as a door between the spacecraft's pressurized interior and the vacuum of space or the lunar surface. It's what allows astronauts to step outside safely without losing cabin pressure. Each airlock has a volume of about 13 cubic meters, more than double the space astronauts had inside the Apollo lunar module. That extra room means more flexibility for preparing spacewalks, storing suits, and managing equipment before heading out onto the moon. Even though most of the interior has been completely redesigned, one part seems to have stayed consistent: the airlock. Back in early June 2024, SpaceX released a photo of a Starship HLS airlock mock-up. And interestingly, it looks almost identical to what we're seeing in the latest design. As you can see, the walls curve a little, and the floor is dark and tough, probably to handle any dirt or scratches. The ceiling is smooth and rounded, helping keep the air inside safe and secure. This room is all about helping astronauts get in and out of their spacesuits before stepping onto the moon. The walls are covered with white, hexagon-shaped pads that look like a honeycomb. These soft pads are there to protect the astronauts' bulky spacesuits if they bump into the walls. It's like having cushions to avoid accidents. The rest of the wall is smooth and white, with some lines and holes where parts can be added or fixed later. This shows it's a test version that can be improved. On one side, there's a big black fabric door that looks like a strong curtain with straps. This is just a temporary setup for testing. It's not the real door they'll use in space. The door is kind of low, so astronauts have to bend to go through it, which some people think isn't safe and might change later. The frame around it is made of metal, hinting that the latest version will have a tough sealed hatch to keep air in or out. On the opposite wall, there's a cool control panel with a screen that tilts up. The screen shows a picture of the Starship landing on the moon, with stars in the background. Pretty awesome. Around the screen are buttons, including 2 talk buttons to talk to others and spots to plug in microphones. There are also some red bordered buttons that might be for letting air out of the room, called depressurization, when it's time to go outside. Below the screen, there's a little shelf, maybe for tools or stuff astronauts need. One side wall probably has machines and wires hidden inside to control the air pressure and keep everything working. You can see some seams and brackets, and there's a small vent near the floor to move air around. This part is like the brain of the room, making sure it's safe for astronauts. What's it for? This mock-up was tested in June 2024 at SpaceX's headquarters, where astronauts wore special Axiom EMU spacesuits and practiced moving around. The soft walls and big space helped them test if they could work easily. Since it's just a test, the door and some parts might get upgraded, maybe a taller door or better lights to make it safer and more comfortable. What might come next? In the future, they could add a stronger door, more lights, and maybe handles to help astronauts move. The control panel might get a touchscreen, and the hidden machines could get bigger to support more stuff, like connecting to a space station. So this airlock is like a high-tech dressing room for astronauts with soft walls, a temporary door, a cool control panel, and some hidden gadgets. It's still a work in progress, but it's super exciting because it's helping us get ready to go back to the moon. So what about you? Are you as excited as I am about the latest Starship HLS design? It's amazing to see how far SpaceX has come from that early testbed inside Starship S-22 to what could soon be the vehicle that carries humans back to the moon. I'd love to hear what you think, so let me know your thoughts down in the comments below. The interior may be what captures everyone's attention, but behind that sleek design lies something much bigger, a massive engineering effort that stretches across every part of SpaceX. Because to get humans back to the moon, it's not just about building the cabin. It's about building the entire system that can take them there. To bring Americans back to the moon, SpaceX is developing Starship along 2 parallel paths. The first focuses on the core Starship system itself, the spacecraft, its boosters, and the massive infrastructure that supports it, covering over 90% of the total system cost. The second path is what NASA calls HLS. It builds on the same hardware as the standard Starship, but adapts it for one-purpose landing astronauts on the Moon and bringing them safely back. Both of these development paths rely on SpaceX's massive private investment, and together they're what make the whole lunar plan possible. Since Starship's very first flight in April 2023, SpaceX has been moving fast, running an aggressive test campaign to push the vehicle further with each launch. That approach has already paid off. The program has seen multiple successful ascents of the world's most powerful rocket, plus launches, catches, and reuses of the booster, all essential steps toward achieving a rapid launch cadence for lunar missions. SpaceX has even managed to transfer around 5 metric tons of cryogenic propellant in orbit, a first-of-its-kind demonstration that paves the way for full-scale fuel transfers in deep space. Add to that successful in-space restarts of the Raptor engines, crucial for lunar maneuvers, and controlled re-entries through Earth's atmosphere, and it's clear that Starship is quickly maturing into the vehicle SpaceX needs to reach the Moon and beyond.